In previous videos, we looked at identifying when there's a linear relationship present, as well as creating a regression line and finding the equation to describe that regression line. In this video, we're going to look at using the regression line in order to make predictions. So if we're given the value for one variable, we can estimate the other variable by using our equation. Interpolation is a method of predicting a value that's within the domain or range of the values or the data set, and extrapolation is when we predict outside of the domain and or range of the data set. It's worth noting that it's harder to make predictions outside of the given domain or range of values because it's hard to know whether or not the relationship will exist between the variables outside of that domain and range, and the model or relationship may or may not hold. So it's always good to think critically about predictions and what sort of limitations exist for your model. In the next example, we're going to look at a scatter plot that we've previously created, use that scatter plot as well as the data to come up with the correlation coefficient and the line of best fit, and use that line of best fit in order to make some predictions. Recall our cricket chirps versus temperature example. We have a column for the number of cricket chirps in a 15-second period given for a temperature in degrees Fahrenheit. The first thing we want to do is calculate or find the regression coefficient R. Now recall the manual method that we did previously, where using our values for C and T, we can calculate the product of each of the C times T values, all of the C squareds as well as T squareds, and the sum of each of these columns. Instead of filling this all out by hand, I'm going to take the opportunity to draw on some of our skills from Math 145 with Excel and cell referencing. We can look at the same information in Excel where we have all the data points of C and T given. And first thing we should do is perhaps identify the value for n. So we know that n is a number of data points and we can calculate it by using a counter. So there's a function built into Excel, count, and if we highlight all the data points, it will tell us how many points there are. And we can see here that there are 9 points. That's helpful, especially if you have a very large data set and it's difficult to count the number of rows. Now, remember that equations in Excel, when we want to make a calculation, begin with the equal sign. If we want to calculate C times T, you can click on where your C value is, so in this case 44, and multiply it by the relevant T value, and that results in the equation B2 star C2. Remember, star is for multiplication. If you press equals, that will give us 3,542. Of course, we could have calculated this value and written it on our chart manually, but this is going to save us a little bit of time by using Excel. Now, going to the bottom right corner, you can see the plus sign, which is the fill handle. And if you drag down this box, it will fill the same equation into each of the values in your column. Now, I always like to check if whether or not I filled into the cell is relevant. So if I double click, you can see that it's using cell B9 and multiplying it by C9, which is what we want in this column for the product of the two values. Now we can perform a similar calculation for C squared. So again, you start with equals, press on C, or click on the relevant C value, and that's in B2, and we use an exponent, so the little hat and a 2. Remember, you're going to find that hat on your keyboard by doing Shift and the number 6. Press Enter, and we can use the fill handle again in order to replicate that formula. Now do the same thing for T squared equals your T value in C2, the power of 2, And of course, when you're cell referencing, depending on where you copy and paste your data or how you format your table, you need to make sure that you're referencing the correct values. So it may be different if more than one person in the class is setting up their table slightly differently. You need to reference the correct cells, and you may have different formulas in Excel. Now, what we need to do is figure out the sum or totals of each of these columns, and those totals will appear in this very last row. So we say equals sum, and the sum operator in Excel expects a range of values. So you can tell it which values you want to add up. So we want to add up everything in column B from B2 to B10, and you can see that there's a semicolon. We've used this operator before in Math 145. Now when you press enter, it will give you the total. And because we're interested in the total of all the columns, I can use the fill handle in the horizontal direction and copy and paste that formula or fill it into the other cells. Now it's good to check that you're actually summing the correct values. So if you double click on some of these, you can verify with which cells are highlighted to see which ones you're actually adding up. So now I have the totals for C, T, C times T, C squared, T squared, and a value for N. One thing I did here is adjust the width of the columns. So by clicking between two column titles, you can adjust how wide the column is. And sometimes there are more values or decimal places available in the calculation than what is initially showing if you have a very narrow column. So it's worth sometimes checking that the full value is showing. Now I'm going to transfer the totals over to my worksheet. Now we can calculate the value of R. Recall our equation for R. We have that it's equal to 9 multiplied by 19,037.8 minus 279.9 multiplied by 592.5 all over the square root of 9 times 9,239.41 minus 279.9 squared multiplied by another square root. So we get 9 times 39,778.75 minus 592.5 squared. So notice I'm fixing up my square root signs so that they are going over everything that's supposed to be under them, and also my fraction line. Now we can calculate this all in one step on our calculators, making sure that you use brackets around the top and bottom of your equation. And we get an R value of 0.950923378, which we can round to 3 decimal places, 0.951. In part B, we're asked to determine the equation of the line of best fit. For this, we must use our formula for the slope and y-intercept and then put it into the equation of a line. Now pause this video and take a few moments to fill in the equations and determine the value of your slope and y-intercept, and then confirm your results with what's on this sheet. So remember that x refers to your independent variable and y refers to your dependent variable, and in terms of our c and t values, x is equal to c and y is equal to t. So we plug in our values and we find that the slope is equal to 1.143046878 and the y-intercept is equal to 30.2771865. Therefore, we can summarize the equation of our line of best fit as t is equal to 1.143 C plus 30.277 if we round the slope and y-intercept to 3 decimal places. In the next two parts of this question, we're going to use this equation in order to make predictions about the number of cricket chirps and temperature. The graph here of the cricket chirps versus temperature summarizes the idea of interpolation versus extrapolation very well. You can see that we have our scatter plot, which we found earlier, as well as the regression line, which we now know the equation of. And we can identify the domain and range of our data set. So we have a domain here that is the x values that our data falls within, and then the range is the y values. Any predictions that occur within the domain and range of our data is called interpolation, and any predictions made outside of the range and domain of our data is called extrapolation. So let's make some predictions. So we're going to make some predictions. It says, use the line of best fit from part B to predict the temperature when the crickets are chirping 40 times in 15 seconds. Would this prediction be interpolation or extrapolation? So what we're looking to do is find T for C is equal to 40. And looking at our graph, we can see that at 40 seconds, that falls within the domain of our function, and this would be a prediction using interpolation. Using the equation for our regression line and substituting 40 in for C, we get 75.997, which is approximately 76 degrees Fahrenheit. Part D says use the line of best fit from part B to predict the number of chirps crickets will make in 15 seconds at 35 degrees Fahrenheit. And would this prediction be interpolation or extrapolation? So let's check it out. So we're looking to find the value of C when T is equal to 35. When T is equal to 35 degrees, you can see here that we can estimate the value of the number of chirps. It looks like it lies somewhere between 0 and 10. Let's calculate it. Now using our equation, we can plug in 35 and find the value of C. Using some algebra, we can solve for C. And C is equal to 35 minus 30.277 divided by 1.143, which is calculated to be 4.132. Because 35 degrees Fahrenheit is outside of the range for the values of T of our data set, this is an extrapolation problem. And we can see that the cricket would be predicted to chirp 4 times in 15 seconds at 35 degrees Fahrenheit. It's great to be able to make predictions, but it's important to know whether or not these predictions seem reasonable, and that depends on what you are modeling. Although using our model we were able to make a prediction for the number of chirps in 15 seconds at 35 degrees Fahrenheit, it's believed that generally crickets stop chirping altogether when it's below 50 degrees. So you could say that our model is actually not appropriate in this case for when we are below 50 degrees Fahrenheit. Let's look at performing the same example in Excel, so fully in Excel this time. Remember, we've already entered the data into Excel when I showed you how to calculate the products and squared values as well as each of the totals. But now we're going to make a scatter plot, come up with the trend line, as well as the regression coefficient and equation of the regression line using Excel. Step 1 says enter the data into Excel in cells A1 to B10. Once you have the data entered into Excel, you want to highlight all your data and create a scatter plot. In order to create a scatter plot, we select your data, insert, or go to recommended charts, and select scatter. And I'll show you that now in Excel. Then you want to go to the insert group, select insert, XY scatter, and the first option where we are only showing the points. And if you recall from Math 145, we often created charts and moved them to their own sheet. Here I'm going to keep my chart right next to my data, but if you prefer to move it to its own sheet, you can right click and say Move Chart and select New Sheet. And that will make a full page title, full page chart rather. I'm going to cancel that. Now, what we want to do is insert a trend line. In order to insert a trend line, you select the data points. You can right click on them and say Add Trend Line. We select that, you can see a line of best fit appears, as well as some options. So in our options, we're able to select linear, and we can also look to the bottom of our options where we're able to display the equation on the chart, and also, if you like, display the R squared value. R squared is simply your correlation coefficient, lowercase r and squared. It gives you an idea of the variability. So here you can see I can move my equation around so I can view it better outside of the data and the scatter plot. And what's really great to notice is that the slope and the y-intercept are the exact same values that we calculated when we calculated the values by hand. And if you were to square your correlation coefficient R that we found earlier, it is equal to 0.9043. So we can see that this line of best fit is a great approximation of our data, and it doesn't have much variability vertically. If you ever decide you want to change something about your trend line, you can right click on it and say Format Trend Line, and these options will reappear, and you can explore other possible trends, so potentially exponential or logarithmic curves, polynomial, and so on. And I'm going to stick with linear in this case, but later in this course, we're going to look at nonlinear regression, where we will be using some of these other options. Recall how we're able to edit our chart as well. When you click on your chart on the Design tab, we're able to add charts elements such as axis titles and a chart title. You can see we can put it above, and if you click on these options, you're able to edit the text. So we can insert a vertical and a horizontal axis title. Make sure when you insert these that you include the units, so temperature, and that's in degrees Fahrenheit. Your symbol for degrees you find under the insert group. Go to symbols, and there is a degree symbol which you can double click on to insert it, and Fahrenheit close brackets. So that's a little refresher on how to create graphs in Excel. And another thing I wanted to show you is how to find the correlation coefficient. So if we want to find the R value, it uses a built-in function in Excel called Pearson. So type in Pearson, open bracket, and Pearson expects to receive the values from your data. So the first array would be your independent values, and the second array would be the dependent values, and you can press enter and we can see it's the same value that we calculated earlier. So that's a fast way to check your results when you're performing calculations by hand. And if you do require R squared, edit this, it's good to make sure that you know how to put superscripts in as well. So you can make the 2 a superscript. R squared is just equal to your Pearson value squared. And that's the value that is shown on the graph as well. Notice all these values have been rounded to a certain number of decimal places. So if you were to perform linear regression using Excel instead of by hand, you would use this formula for your regression line in order to make predictions. So make sure you practice this. There's some questions on D2L for recommended homework. You can practice using Excel as well as making the calculations by hand and check the methods against each other. And contact your instructor if you have any questions.